Thank you, everyone, and good afternoon, I suppose. I'm Mohamed Wehbi. I'm the Technical Director at Geobear, and today I'll be talking to you about the use of geopolymer injections to stabilize railway embankments. Now, a lot of you may have come across Geobear or the solutions that we offer in Geobear, but geopolymer injections, in essence, has been used widely to address ground settlement problems and subsidence issues. And mainly, it was focused on increasing the bearing capacity of foundations. So that's the main use of it, and it's been used for some time now in this application, and there's a lot of cases and studies that demonstrates this. Now, one of the things that we thought of that we wanted to take this technology forward with is to basically try to adapt this technology to address embankment issues and slope stabilization issues. And the reason for this is because we believe that this technology will be able to provide minimum disruption to maintenance work for embankment stabilization, because a lot of the work involving embankment stabilization tends to be very disruptive. So this technology allows you to take away that factor and do the work very smoothly in very short possessions. Okay? So I'm not going to go into the details of what geopolymers are. Unfortunately, the time span or the time slot that I've got here doesn't allow me to do though. But so moving on, sorry. So what we've decided to do was to basically try to apply this technology on the Heritage Railway, where there is an embankment instability problem, and basically test it and see the performance, the long-term performance that this solution would provide. So we've decided to go with a site that is located on the Severn Valley Railway, a Heritage Railway in Kidderminster. And what they've got there is a section, is about 80-meter section that has been experiencing significant settlement due to a slope instability problem. And you can even see a 300 mil deviation, it's quite visible on the picture, a 300 mil deviation of trench geometry as a result of a moving embankment, a slope stability. Now to the left-hand side of this picture, to the left-hand side from, if you're facing the picture, there's the River Severn, and basically the embankment is just slope moving towards the river, okay? As a result of the movement, they had to put a speed restriction, and basically a 5 miles an hour speed restriction or 10 miles an hour speed restriction. And what we've done, we've basically taken all the ground information there, and we tried to come up with a design philosophy that allows us to install this solution and monitor it. Now, the embankment, basically, you can see there's a valley, and there's the valley, and then after the valley you get the railway, and then the railway next to the river. The embankment is about 4 to 5 meter high, roughly 5.5 meter high, and the worst part of, or the worst performing section of the embankment is basically the highest one. The slope was around 23 degrees, so nothing unusual. It's a very old Victorian railway there. And the interesting thing, and the reason why we selected this particular site, is that it already had instrumentation and that has been monitoring the movement of the embankment. So there's tilt sensors there that have been monitoring different sections of the embankment, and also they also have inclinometers embedded within the embankment that is measuring the movement of the core of the embankment. So that's why we essentially wanted to go and target this particular track, because it has the problem, a severe problem. It has this nice, comfortable environment where we can test things and try to do it. And at the same time, it has great monitoring on it installed, so we can compare the effect of the injections before and after the injections. Okay. So what is the first thing we started with is to look at the ground model. So what's the embankment is made of? So we've looked at the ground investigation there, and the embankment essentially consists of a thick layer of, the track is resting on a thick layer of ashy fill, very loose ashy fill, and then followed by a firm layer of clay. And within that firm layer of clay, there is a very thin layer of very soft clay, which is perceived or interpreted as a slip surface, a pre-existing slip surface, very, very soft clay, layer of clay, about 10 centimeter thick. And we believe that the problem has been manifested or been driven by that pre-existing shear surface. Okay, so there's a lot of modeling that has been carried out. Some modeling has been carried out by external consultancies, which have actually demonstrated that this slip surface is contributing to is driving the main problem, It's also worth noting that there is a water flow going through the embankment. So there is a problem with water flow going through the embankment towards the river. So that's a contributing factor. And also you've got this pre-existing slip surface. The modeling that has been done by external consultancies have shown that the factor of safety of the embankment is around 0.8, which is pretty unacceptable. I mean, you can see it visually from the pictures and the problems that they've been experiencing. So how can we design for it? Well, the simple solution is to go onto the embankment and flood the whole thing with geopolymer, inject as much as we can. However, in the real world, that's not really a practical way of doing things, because obviously it will basically take the non-disruptive element out of the equation. So it's not, it's quite disruptive, because if you're going to inject a lot of polymer into the embankment, and also it's not uneconomical, so no client will take that. So we need to put a realistic design that mimics, a real job. Okay, so what we've done our own modeling, not for the sake of being cool or trying to produce some interesting graphs, but there's a very logical reason why we've decided to do that, is because we needed to understand what is the area that we needed to treat that gives us the most cost-effective solution. Do we treat the whole embankment slip, the whole slip surface, or do we treat a particular section? So we ran a lot of simulations that allowed us to test, what would be the effect with different treatments. And we basically used all the parameters that we had from the geotechnical investigation, and we've also learned that we needed to increase the stiffness of, or the shear strength of that slip surface to up to 100 kPa, which is quite a significant and substantial increase. And what we've learned from the modeling is that if we treated the dashed line, the area within the red dashed line, that will give us the most optimum design solution, that will give us the most cost-effective way to treat the embankment. And that would allow us just to push the embankment factor of safety to around 1.2, a factor of 1.2, just enough to get us to where we want, for the sake of understanding what's the effect. Okay? So based on that information, we developed an injection plan that targets the shear slip surface, but also we've done some injections underneath the track in the loose ash to also compact it and get it to a good condition. Okay, so following the design, we basically went on site last year in July time, where we've actually spent 2 days on the track where we treated a 10-meter section. So we picked up the worst section within that 80 meter. So that's the 10-meter section, and we've carried out the work. The work was carried out on the 25th and 26th of July, and using our mobile injection unit. So we've got this injection unit where it gets attached to a normal train. And from that injection unit, there's all the equipment and the hoses of injections comes out of it. Okay, and we basically installed the injections via 12 millimeter diameter hole. So every injection tube is only 12 millimeter diameter hole. So that's how big it is really. So you drill that much and you insert an injection tube with that size. And then you inject the material. So we injected about 2.5 tons of material, and we installed 136 injection tubes. You can see them here in the pictures, where you can see, do you see these, small, tiny metallic rods? These are the injection tubes. So we've injected underneath the trap bed and also on the embankment shoulder, in accordance to what the modeling have actually shown us. And then following the work, we finished the work. We've basically carried out dynamic probing to understand the short-term improvement. So what we've improved on the short term, the dynamic probing will give us an idea of what the level of improvement in the shear strength that we've achieved. But also we've monitored the track movement from the tilt sensors and the inclinometer sensors for a period of 6 months. And we're still doing that as we speak. We managed to complete the work in 2 10-hour shifts. So we treated that 10 meter section and installed 2.5 tons of material. The original plan was to basically inject 5 tons of material, but unfortunately, due to time restrictions, we had to kind of squeeze that out a little bit. And we said, okay, that's a good opportunity to test how much we can actually go with this design solution. Okay, now performance. So as I mentioned earlier, we've carried out 2 assessments. One assessment on the short term using dynamic probing. Dynamic probing will give us a number of blow counts that can be converted to a shear strength, and that would tell us how much we've managed to improve the situation with. So we've carried out one dynamic probing before the injections and two dynamic probing after the injections. And what the graph here shows you is the converted dynamic probing values to a shear strength, to undrained shear strength values. So you can see the top layer where you've got this head deposit layer, which is the firm clay, has quite a substantially high undrained shear strength. So previously it was peaking at about 100 kPa, and then after the injections, we managed to improve that to 150. So anyway, it's good. It's a good layer anyway. It's a firm clay layer. It's not really driving anything, but it's gained out of this. But then you can see the shear zone area where the shear zone before the treatment, where you can see in the red graph, it had an undrained shear strength as low as 20 kPa. Very, very low undrained shear strength. That's before the treatment. After the treatment, we managed to get it to an average about just over 100 kPa. So what we've planned for, we've kind of managed to achieve on the short term. So you can see an improvement there. And there was also some minor improvement to the loose ashy fill. So we got it compacted a little bit and increased the angle friction, which is not showing here in this particular case. So using the information that we've obtained from the dynamic probing, we've kind of reran our models to see are we can really achieve what we should achieve from a factor of safety. And it looks like, based on the information that we've captured, we should achieve a factor of safety of about 1.2 for that treated section. Now, it's important to note out you've got an 80-meter problematic section and you're only treating 10 meters. So that's not going to solve the problem entirely, but it's just a start. It's a beginning, okay? The whole aim is that, okay, if the results are promising, we'll continue with the remainder of the section. Okay, so these are the tilt sensors. They were monitoring live, and we basically treated around the central section, the central area, where you can see the red dashed area. Okay, and what we've learned, so before the treatment, the rate of deterioration or rate of movement of the tilt sensor was around 1.75 millimeter a month. So every month this was moving by this much. And after the treatment, this has gone down to around 0.4 millimeter a month. So that's roughly about 75% reduction in the rate of movement, how much movement that you're getting, how fast it's moving compared to before and after the injections. We would have achieved a further improvement if we were able to achieve to install the 5 tons of material, but it's good that we kind of understand what happens if we don't get the full picture. Okay? And that's the most interesting part. So the inclinometer readings. So the inclinometer readings, they were running for almost 2 years before we came in. And from that, we picked up a similar sort of time period before and after the installation that has taken place. So we can have a similar sort of water or rainfall quantity going through the embankment. So similar conditions, so it's not biased in that sense. And from that, if you look at the readings of the inclinometer readings in November 2021, it was peaking around 18 mil. And this happens to be around the area of the slip surface. You can see it here quite clearly. And then in February 2021, the reading moved to about to 21 millimeters. So that's a rate of movement of around 1 millimeter a month. That's the core of the embankment moving towards the river by 1 millimeter a month before the treatment. Following the treatment, we've compared a similar sort of time period where you've got in September 2021, the movement was about 31 millimeter. And then in February, it moved to 32 millimeters. So that gives me a rate of movement of around 0.3 millimeter a month, roughly. So that's about 72% reduction in the rate of movements as pre and post the injections, which is seen as very promising. And the beauty in all of this, if you go back now to the track where we've done the treatment, you're not going to notice anything. You're not going to see any trace of our work. You wouldn't even know that we've actually done the work. And this was very important to the Heritage Railway operator because they didn't want to put anything that would ruin the scenery in that sense, or kind of, ruin the aesthetic of the scenery. So it was all underground, so all of it is buried, nothing had been visible, and you wouldn't even see the polymer on the surface. So it's all underground at depth. I've also compared the amount of rainfall just to make sure that, okay, we're not really getting false readings here because there's less rainfall here or less rainfall there. Before the treatment, during the time period of September to February 2021 to 2022, we had a total rainfall about 342 mil. That's the total rainfall in that area. After the treatment, in a similar period from September to February, it's actually slightly higher than what it was been there before the treatment. In the same time period, it was about 370 mil of total rainfall. So the rainfall is quite similar in both time periods where we've done the comparison. So we can assume that, water content hasn't really made a big difference in this particular instance. So we are still currently monitoring the situation, seeing how the track is progressing. Now, as I've been told, that the track has been tamped, lifted, got to the right position, and they removed the speed restriction. So now is the real test to see how long it's going to stand, that 10 meter section, and how long it will last before we have to intervene again and get a full assessment of whether this technology have actually achieved the desired objectives. In conclusion, so at least on the short term, we've demonstrated that this technology is capable of reducing the rate of movement. Obviously, design is an important element into this. Just going in and deciding to inject a large quantity of geopolymer is not going to really solve the solution in the right way, because there's a lot of other things that you need to consider when you're doing that. So, for example, one of the main considerations that we had to look into was if you inject a lot of polymer, you could effectively create a dam, because you're really filling all that pore space within the embankment. So we don't want to create a dam. We still want water to flow through the embankment. So going for very high quantity is not really a sensible solution. So engineering plays a good part of it in all of this. The probing, as I showed in the short term, showed a significant improvement, a substantial improvement in the undrained shear strength, which is a good sign. The long-term monitoring, whether you're talking about the tilt sensors or the inclinometer sensors, they both showed a reduction in the rate of movement by around 70%. And this is the first of its type. So this is the first time that we've utilized this technology in this particular application in the UK. So it's a good starting point, and hopefully this will provide future geotechnical engineers with an additional solution that they can consider when they were thinking about earthwork remediation and renewal. And that concludes my presentation. Thank you all.